We have David Sobral from the Leiden Observatory. He's been there doing his first postdoc, like for 6 months or so, after he defended the thesis in the University of Edinburgh. So, David.
Thank you. Can you hear me all right? Yeah. Well, it's great to have this opportunity to tell you a little bit of my work over the last about 3 to 4 years, and which has been mostly looking at the evolution of star-forming galaxies roughly in the last 11 gigayears from a large and multi-epoch H-alpha survey, which I'll be describing in a few minutes. Now, we all know that we seem to be living in a universe which started with the Big Bang, and that's dominated by something we have really no idea what it is, which seems to be dark energy, and even the matter component of it, most of it is dark, so it's something we call dark matter. And the good thing about it is that if you ignore all the baryons and all the other physics, you just concentrate on gravity, you get a really nice supercomputer, you run a nice detailed simulation, and you seem to recover something that at least looks like our own universe. So at least the sort of dark matter component of everything that's happened since the Big Bang seems to be sort of relatively well understood. The problem is, of course, if you want to go beyond this and you want to start asking much more difficult questions, such as how, when, where, and through which mechanisms galaxies form and evolve. And the problem is, to do this, you need to then care about baryons, and you need to care about complicated things such as star formation and putting all the laws of physics into your understanding. And particularly star formation is not only difficult to understand and study theoretically, but even observationally, it's an issue because stars tend to form in these very dusty and obscured environments. So if you want to study these regions, you really need to go into the infrared, far infrared. Otherwise, you'll be missing most of them. And this is true in even our own galaxy. But once you then start going out and look for star formation signatures in other galaxies and in very distant ones, you can no longer resolve individual stars. And then you go even further, you can no longer resolve individual star-forming regions. So most times when you look at very distant galaxies and you're trying to understand how much stars they're forming, you're really looking sort of the integrated thing, the integrated quantity. So we rely on signatures of very recent star formation in these distant galaxies. But what we're actually seeing, just an example here, is we're probing very massive stars that are very short-lived. So if you see them, it means that star formation is very recent. But then you need something which we call an IMF to extrapolate and to get an idea of the total star formation that is occurring in the galaxy. And you can use several different tracers to do this. And the most obvious one is probably UV, because if you look at the UV, and if it's not highly obscured, you should be able to see the light directly coming from these very massive blue stars, which are short-lived. But again, because of problems with this extinction, which can be quite high, and it's not just a problem of correcting for it, it's a problem about missing the galaxies completely. The good thing is that as UV light is absorbed, the energy is then re-emitted through a variety of processes. So on one hand, UV photons ionize things, so you can look at emission lines from around the region, but also dust grains, they get warmer and they then re-emit as black bodies in the far infrared. So you can look the far infrared to estimate star formation rates as well. And then there's other varieties of things such as radio, not only because it probes sort of supernova rates, and also the correlation that you have with far infrared. Now, the thing is, there are loads of ways of doing this, but they're all somehow affected by different extinctions, different biases, and for some of them, you can only look at a particular redshift window. So traditionally what people did was trying to put all of this together and try to construct the star formation history of the universe with all these different indicators put into it. And the tremendous work that's been done has led to quite an amazing progress in doing so, which is shown here in this traditional sort of Madao plot, where you can see as a function of increasing redshift how the amount of star formation that is occurring in a given volume of the universe has changed. So we are quite confident that it rose quite dramatically up to redshift about 1, and then what happens next is a bit of a blur. But even at lower redshifts, the fact that you're combining everything, you're putting everything together, leads to this huge scatter, which we really should try to sort of eliminate or constrain better. The other side of the picture, which you can look at, is to, instead of looking at star-forming galaxies, you can look at all the galaxies that are in the universe as a function of cosmic time, and you measure their stellar masses. And with that, you can derive stellar mass functions, and if you integrate them, you get sort of the total stellar mass density that exists in a given volume of the universe as a function of this cosmic time. And this is what people have been finding, is that most of the evolution has been sort of in the number density of galaxies, that the typical mass of galaxies has remained almost constant for most of the history of the universe. And this gives you a picture of how the stellar mass density evolves. Now, if you have a measurement of the star formation history of the universe and the stellar mass density evolution of the universe, they ought to be compatible. So the thing is, if you know the history of star formation in the universe and you integrate that, you should be able to recover this sort of evolution. And traditionally, what people find is that you don't. If you just go on and look at all the different indicators, you take somehow a median fit to it, and you try to compare that with the actual measurements of the stellar mass density, what you obtain is an overestimation of the stellar mass density in the universe. Now, there's a lot of different reasons why this is happening. It could be just because of different selection effects. Maybe you're missing mass. Maybe you're overestimating star formation rate. Maybe the assumption that there's a single IMF that can work is wrong. So what's really going on here? And what do we really need to improve our understanding? And I'm going to argue that you can do this if you try to use a single star formation rate tracer that can be applied all the way up to redshift about 3. So getting the bulk of the history of the universe, the last 11 to 12 gigayears, something that's sufficiently well calibrated and sensitive. And with that, you can take what I'll call part 1, which is really improving the star formation history. But then if you do that, and if you gather large enough samples over large enough volumes, you can not only do this and improve our understanding, but we can then try to explain why the star formation history is the way it is. And I'm going to do this using H-alpha, which obviously fits the bill very well. It's very sensitive. It provides a good selection of star-forming galaxies, and it's been traditionally used in the local universe. And this has become quite a powerful tool now that there's wide-field near-infrared cameras available. And you can then combine these things to do narrowband surveys. And for those not familiar with the narrowband survey, what you do is you take your wide-field near-infrared camera or optical camera, you get a narrowband filter, and by that I mean about 100 angstroms wide. You image the sky, and then you image the sky with the broadband filter, so you can remove the continuum. And the things you're left with are potential line emitters. You can see an example here. Imaging in a narrow band, you take out the broadband scale one, and the things that are left are potential line emitters. And this is just an example of how to get the H-alpha emission line, redshift 2.2. When it gets there, it produces an excess, and you can select it. So the really nice thing about this is that you can target really, really large areas, which wasn't possible before. And people have started doing this and really improving in the last couple of years. Before these studies from 2008, 2010, the largest sample of H-alpha emitters selected this way was about 4 to 5 galaxies. And so this already constitutes something like a factor of 10 larger samples. But still not enough. And it's not enough because studies are finding things which really don't agree. Some authors are finding very steep finite slope of the luminosity function. Others are finding something which is very shallow. And the number statistics here is still quite a problem. The other problem is even when you have very good number statistics, things don't necessarily agree. And this is a problem of the fact that people usually focus on a single redshift. They do a survey. They use their own aperture measurements, their own selection criteria. And when they try to compare with other studies, there's differences. So if there are differences even in the same sort of redshift and epoch, how can you be sure that by comparing with another epoch, you're really measuring evolution? Aren't you just measuring the fact that you're using a different method? So to really address these two questions of the need for larger samples and the need for something that is completely self-consistent, we've been conducting a survey which we call HISELS, the High Redshift Emission Line Survey, to do this in a completely self-consistent way. So we have these 4 narrowband filters. This one is actually on Subaru. These 3 are on UCURT and Mauna Kea. And they get H-alpha emission at these 4 different redshifts. So 0.4, 0.8, 1.5, and 2.2, really tracing basically the last 11 gigayears of evolution. And the nice thing, again, is that we use the same reduction, the same analysis for the entire sample. And here, I'm just going to be concentrating on a part of the survey. The survey is actually covering 5 square degrees, but I'll be only talking about the results that we've obtained over the cosmos and the UDS field, which are already about 2 square degrees. And obviously, they constitute quite a large effort and a lot of observing time, with about 25 nights on UCURT, more VLT time and Subaru time as well to do this very well. Now, to give you an idea of what we are talking about, we're trying, and this is what we actually achieved, going down to something like a Milky Way star formation rate, all the way from redshift 0 to 2.2, covering these very large volumes and doing the selection in a completely consistent way, and also sort of measuring the H-alpha emission over the same physical apertures at all redshifts, so we don't introduce bias because of that. And the other unique thing about this is that the filters not only get H-alpha, but they help you select the emitters, because one example is when you look at the H-alpha emission redshift 2.2, which you find as an excess here, then you can use the imaging on the other filters to get the O3 emission line, the O2 emission line, because they match the other strong emission lines there as well. And at redshift 1.5, you get H beta in the narrowband J filter and the O2 line in here, and another combination for redshift 0.8. So that really helps you getting a much cleaner sample, and to also, particularly for redshift 1.47, this thing works so well, and you can go so deep in Subaru that you can even forget about photometric redshifts or color selections to differentiate between emitters. What you do is you basically require that something's a narrowband emitter in the narrowband H filter and in the narrowband 921 in Subaru. And this is just an example of the same very small region of the sky. Where you do this, you imagine broadband, narrowband, and the things that are dual emitters. And with this technique are for sure H-alpha and O2 emitters at the redshift you're looking at. And so very briefly, I really don't want to go into details, but you can ask them later if you want. This is just the schematics of how we go on from selecting the line emitters up here to then distinguish between them, because the narrowband filters can get any emission line. It's not just H-alpha. So you need to particularly here, because we're interested in H-alpha emitters, you need to use photometric redshifts and color selections to distinguish them. But you can make use of the fact that for some redshifts you have dual or triple narrowband line confirmations. And then you also use, and we've also done some spectroscopic follow-up to be sure of our selection and to get a hold of how complete and contaminated we are. And these are the numbers of H-alpha emitters that we get. And just to highlight the fact that the largest samples before this were about 50 H-alpha emitters, and we now basically raised the sample by an order of magnitude over 500. And the other thing is that we'll be publishing these catalogs. So if you're interested in doing science with not only the H-alpha emitters, but with any other emitters, you'll be able to do that. And I guess this is the sort of first main result of what you can do, is derive the H-alpha luminosity function and how it evolves from redshift 0, which you can see over here, redshift 0.4, 0.8, 1.5, and 2.2. And I guess the clearest thing about this is this very strong luminosity evolution that you see here. And the other thing that's probably even obvious to the naked eye is that the phaeton slope is not really steepening from redshift 0 to 2.2. And I'll show you in the next slide that if we do a fit to this, what we find is something that looks very, very constant, alpha about minus 1.60, which is actually very similar to what the people looking at the UV are finding, something that's not really steepening, at least up to redshift 2. Maybe it does at much higher redshift. But it's a really good approximation to just use this for the last 11 gig years. The thing that's really changing, and that's quite striking, is L star, sort of the break, yes? Sure. So we're using all the data that we have. Obviously, a redshift 0.4, this is extremely well constrained, right? And for here, you can see L star is about here, so you still have a few points. And the other thing is that we've combined with the other studies that go deeper, but we didn't use them for the fit. So the other thing is that if this is just the fit to our own data, which our data stops about here, redshift 2.2. There's deeper data here, but it wasn't included in the fit, but it fit. So it's consistent with the fit to our data, but we haven't used it. Yeah, so the details are in the paper where we use a metallicity dependence to do that. So we use the equivalent width as a way to remove N2. So basically, what we do is for the very metal rich, we remove more N2 from our measurement, and for the very metal poor, we remove less. So, but that's a relation that we calibrate with SDSS. That's the best we can do. But yes, so the other thing, in this case, we have done a detailed study of how extinction varies within our samples, which is consistent, at least to a first approximation, with about a 1 magnitude of extinction. And for this analysis, we assumed one uniform 1 magnitude of extinction for all H-alpha emitters. But we're working on sort of the details of how that approximation works and where it breaks. But I'll show you that slides. So the other thing we can parameterize this L star evolution, something like 0.5 of redshift, which fits the data very well. And if you're interested in seeing how, for a fixed phaeton slope, how the normalization and L star varies, so it looks like both L star and phi star go up slightly up to about redshift 1, and then L star continues to evolve, but the number density goes down. So this is the picture that we're getting from our data. And then when you, again, using the correction of 1 magnitude of extinction, and we also do a correction for AGN, which I'll explain a little bit in a few minutes. This is the star formation history that you get, now based solely on H-alpha and with our completely self-consistent analysis. And what you can do is fit the very simple parameterization as a function of redshift. This is how it looks like, or something as a function of time, which we will see it's useful if you want to then compare what this star formation history of the universe implies to the growth of stellar mass in the universe. And what it does is that it agrees really quite nicely with the observation. So if you just take this very simple fit from our H-alpha star formation history of the universe, and you compare it with the measurements of the stellar mass density evolution, we can get a really nice fit, even without changing the IMF or with any of the arguments. So it looks like with this H-alpha analysis, we're getting the bulk of the stellar mass assembly of the universe, at least to redshift about 2.2. And this is just a summary of the things we find in this sort of part 1, which aims at really trying to derive a much neater and better star formation history of the universe and parameterizing the main things that are changing. But of course, even more interesting than just quantifying all this is asking the question why. Why is this happening in the way it is? And to do this, I won't go into much details on any single item, but I would like to give you sort of an overview of the things we've done and are doing to try to answer these questions, particularly looking at the role of nature and nurture, the roles of stellar mass and environment, the fact that some sources are AGN, star forming, and looking at dust extinction and clustering. And the roles of mass and environment have been widely realized to be important. At redshift 0, if you look at SDSS, you find very striking relations between the fraction of star-forming galaxies and the density, or the density here, or stellar mass here, meaning if you look at very massive galaxies, they'll likely be red and dead. If you look at the least massive, they'll be blue and star-forming. And there's the same similar relation with environment. If you look at the field, you'll see more star-forming galaxies. If you look in the cluster, they'll be red and dead. Whether this is true at high redshift or when this really sort of starts happening is not clear. And just to illustrate that, if you're not familiar with what people have been doing in the last few years, these are the relations that we find in SDSS. So if you look at the star-forming fraction as a function of sort of local density, it goes down, and also the typical star formation rate goes down. And a few years ago, people have started to try to do this at high redshift with very small fields. That's true, and they realized, or they found this tentative complete inversion of the relation. So they claimed that at redshift about 1, this was completely reversed. Then other people came along and started focusing on around regions which we know they had clusters at redshift 1, and they started finding things which were different. And then a lot of people have done a really nice job in targeting very well-known clusters And they conclude the complete opposite. They say, no, it's just like redshift 0. So what exactly is going on? And we've been exploring our data, and this gives you an idea of the power of going to very wide fields for these H-alpha surveys. And particularly in the Cosmos field, we actually hit a really nice supercluster here. These are X-ray detections, and the black squares are our H-alpha emitters and where they are. So you can see some really nice filaments, and you can get a really nice overview of the range of environments. So you can, in a single shot, you probe sort of very dense regions and down to the very poor fields. And something unique that we've done is trying to calibrate what we mean by a specific projected local density. What does it mean? And we've done this simply with looking at the clustering of galaxies and trying to associate our projected local densities with what we would consider to be a rich group, cluster, poor group, and field. And this is important because it gives you an idea of exactly the kind of environments that you're probing, so you can then compare with other people's results. And actually what we find is that by doing this and by identifying sort of the transitions between fields, groups, and clusters and comparing with other results, we find that we can reconcile everything actually, at least first order. If we restrict our analysis to other people's analysis, looking at just the field, then we do see what people would claim a reversal. If we look at the intermediate environments, sort of clusters, but also groups and rich fields, we can also recover the other results. And if you just restrict our analysis to clusters and very dense regions, then we recover the results from redshift 0. So I'd actually argue that we're finding evidences that at least up to redshift 1.5, if you do this properly with a very wide range of environments, you do see something like SDSS, at least up to redshift 1.5, where you see the fraction of star-forming galaxies goes down with increasing environment, and it also goes down with increasing stellar mass. But there are things that you can split, you can start to split very well at redshift 1 between the roles of stellar mass and environment. And two examples are the merger fraction, which we find that it's mostly dependent on environment. But if you're looking at something like color, then it's mostly driven by mass. Environment doesn't really do much. You'll probably you'll see more red galaxies in high-density environments, but that's mostly because of the correlation between mass and environment. But it's mass that's really driving this correlation. So what about AGN? And I haven't talked about this very much, but when we select H-alpha emitters, and we assume most of them are star-forming, that's not necessarily true. A lot of AGN could have strong H-alpha emission. So what we've done is a very detailed analysis, and we've done so redshift 1 and below, and we're working on higher redshifts. So using anything that we can, so spectroscopic redshifts and emission-line ratios when we can. We use some Spitzer color diagnostics. We look at the X-rays, radio, and the conclusion, at least at the redshift 1, is that only about 8, or you can say about 10% of our H-alpha emitters are AGN, any single kind of AGN. And the remaining are basically star-forming. But the interesting thing that we're finding, and this is also why I'm here for an observing run on the TNG, is that this is true when you look at the entire sample, but it's not true when you look at the highest, the most luminous H-alpha emitters, because then it's where you start to find very powerful broadline AGN. And indeed, we're finding a nice correlation. If you go above L star, this is where the AGN start to be more prominent, and where you see a nice relation between H-alpha luminosity and the fraction of broadline AGN, but you also see some things getting more metal rich, more AGN-y dominated, And when you go to lower luminosities, you get more metal-poor things and more things that are basically dominated just by star formation. The other nice thing I think to look at is the morphologies of these star-forming galaxies, and mostly because you could think that the star formation history of the universe, at least naively, could be just driven by the fact that there are less mergers as time goes on. Is this true? And we do find some really nice disks in our samples, some things which look like mergers. And the other nice thing about our survey is that we're covering the cosmos field and the UDS, so there's plenty of HST data with high resolution to do this. But we're also, and I won't talk about this, but we're also following up these galaxies with Symphony and IFUs to do this, and to look at the rotations and metallicity gradients, etc. But the main result that I would like to highlight from what we've done so far is this relation between the fraction of disks and the fraction of mergers as a function of H-alpha luminosity or star formation rate. And this is an example of redshift about 1. What you find is that if you go to the lowest luminosities, you're basically just looking at an entire population of disks. But when you go above L star, you see mergers rising. And there's a complete domination of mergers at the very, very highest luminosities. And even more interesting is the fact that back in 2009, we sort of tried to look at these relations at two different redshifts. We found them, and we found some tentative evidence that if you account for the evolution in L star, basically if you divide your measured H-alpha luminosity by the typical H-alpha luminosity at that epoch, if that's understandable, you seem to be able to recover a single relation. And this is came out quite strikingly, is that now that we have the information for all these redshifts, if we do it, we can actually recover something that looks like a single relation that holds up to at least redshift 1.5, and which tells you what's the fraction of disks and mergers as a function of the position within a Chester function. So if you divide by L star at each epoch, what this tells you as well is that the transition between being merger dominated and disk dominated is about here, which is about two times L star. And so this is sort of the cartoon of what we're finding, is that any given epoch in the last about 9 billion years, you're basically 10% mergers all the way. There's no real dependence. Once you hit L star, mergers start to rise, and about 2 times L star, they become dominant, and eventually they go up to about 100%. And interestingly is that this even matches what some models of people have done, which sort of tried to look at where is the transition between, in terms of LIR, but you can convert it to star formation rate or H-alpha. Whereas the transition between star formation being normal or disky dominated, or when it becomes merger dominated, then these are the points that we get from this transition here, being at the same place. It seems to agree with these very high detailed hydrodynamic models. And I guess the conclusion that I would just like to highlight is that even though mergers become very important at the highest luminosities, when you look at the entire star formation rate density, they're very insignificant in a way that they do not explain the fall, at least from redshift 1.5 to 0, because they only really account for about 20% at any given time of the total star formation rate that's occurring in the universe. So they're not the cause for this decline. What about dust extinction? And just to answer that question, it's important because it's an important ingredient to getting a star formation rate, because we observe H-alpha luminosity, but we need to correct for it. And the example I'd like to give is from a study we've completed last year, tried to compare galaxies selected in SDSS with the galaxies we're selecting at 1.5, and particularly looking at the ratios between H-alpha and O2. And I think this gives a nice comparison between the two. This is where the SDSS galaxies lie in terms of observed H-alpha luminosity and observed O2 luminosity. This is sort of the lines of what you expect for different extinctions: 0, 1 magnitude, 2 magnitudes, and 3 magnitudes. And this is where the redshift 1.5 galaxies are. So they're very much more luminous in H-alpha and O2, but when you look at the ratios, they're actually consistent still with being, at least the median, about 1 magnitude of extinction. And the other interesting thing that we find is that the relation that people have found between the typical dust extinction and stellar mass seems to hold from redshift 0 to 1.5, which might be useful if you want to get a hold of the dust extinction in a sample of galaxies and you know their typical stellar masses. But we also find a relation that holds from redshift 0 to 1.5 as function of colors, and these are given in this paper, which could be useful at least to get a sort of a statistical idea of the dust extinctions in population of star-forming galaxies. Now, one thing that doesn't hold is a relation between the amount of dust extinction in star-forming galaxies and H-alpha luminosity or H-alpha star formation rate. And this doesn't hold because you'd expect that if this was true from redshift 0 to 1.5, you'd expect, because these galaxies are very luminous in H-alpha, they should be highly dust extincted. They should be here, but they're not. And the other curious thing is that we found that if we scale things by the evolution in L star, the morphologies would fit a single relation. If we do the same for this thing, so basically we rescale the H-alpha star formation rates that we find at redshift 1.5 and rescale by the factor that they've evolved from 1.5 to 0, this is what we find. So if you correct for the luminosity evolution from redshift 0 to 1.5, then our galaxies, despite being very luminous, they look like SDSS galaxies, both in the scatter and the median. And then they do obey this local relation thing, which really highlights something I've always struggled with, is the notion of what is a U-lurg and a lurg. And I think this is quite a nice point to make, is that if you define a U-lurg or a lurg by a fixed luminosity cut, and you say that something that's more than 10 to the 12 is an ultraluminous infrared object, it really isn't if you're talking at different redshifts. It is a redshift 0, but because everything's getting more luminous, if you do the same cut at redshift 2, then you're just looking at a more normal galaxy. So you really should think of something that evolves as a redshift as a function of this L star evolution, and to change the cuts. And finally, something that we've been doing with these very wide and large samples is looking at how star-forming galaxies cluster. And the highlight of our results is that we find a very strong dependence of the clustering as a function of star formation rate, or H-alpha. And if you want to look at something such as the sort of the typical dark matter halo that hosts these galaxies as a function of H-alpha luminosity, we see these trends at least up to redshift 2.2. But I think the interesting thing here is that if you look at a fixed dark matter halo, something which is sort of a Milky Way type dark matter halo, you see that at redshift here 0.24, they sort of produce some H-alpha luminosity. At redshift 0.84, they seem to be able to sort of host more star formation rate. And if you look at redshift 2.2, the same dark matter halo seems to be much more efficient and produce very high star formation rates. And again, if you remember the very strong L star evolution, and again you go on and you try to divide H-alpha luminosities by L star, again you seem to find a single relation, which is probably telling you that if you look at the HST function and you know the location within it that your galaxies reside, you can get a statistical idea of what's the typical dark matter halo which hosts these galaxies. And this entire thing, then trying to combine all these things and why this is, can, I think, probably provide very important clues as to why the star formation history is doing what it does and the relation between all these things. So I'll leave you with the summary, and if you do have questions, please ask. Thank you.
I have a few questions. Can you go back to the end of your first part? So one of the things that wonders me more is that at the beginning of your introduction, you said that there was, and it's correct, no? So that there was go back to the previous one. That one.
This one?
Yes. So at the beginning in your introduction, you said that there was a discrepancy between the inference from the star formation rate history and the amount of mass that you are creating through the cosmic time. No? Now I see your slide here, and your points go through the previous data set. But if you go now, you move to your next slide. You say that you are able to go perfectly through the other data. So what is
it
what
goes
is the
slightly
novelty
lower
here?
Yeah, so I guess the difference is, I think that the main difference is about here. The other fit that's been used, if you go through all the data, it goes through here, which does make quite a big difference around here. And I guess the other thing is how you go on and do this. If you fit to the entire star formation of the universe, then you actually go on to about here, redshift 10. And then you integrate that. But the thing is, you basically propagate all your huge uncertainties at redshift 10. What you can do is you can start at redshift 0 and integrate backwards, because here you have a very good idea of the stellar mass density that exists in the universe, and you'll probably have less uncertainties around here. This is what we've done.
Okay, so what you say is that you were more complete somehow, and that's why your star formation rates were in median smaller than previous samples that were more focused on brighter H-alpha emitters, or so. That's why you get a lower star formation rate as a median value, and then everything fits. This is what you're saying?
I think the thing is, when you're doing a fit to the data that's been obtained in absolutely different ways, it doesn't mean you're going to get the right answer anyway. It's not because any given survey is wrong. I think it's just, if you just combine everything, you simply combine, you don't necessarily get the right answer, right? Because a lot of these surveys are based on very small areas. So most of them, the big problem is cosmic variance. Others is the problem with estimating dust extinction. And so I think I'm not claiming that the H-alpha analysis does better than everything else. What I'm saying is our measurements are completely self-consistent. So at least the evolution that you see shouldn't be because you're looking at a different tracer or you're doing a different analysis. Whether the normalization is completely correct, I wouldn't sort of bet on it. And that's not my point. My point is, even the normalization looks somehow okay. It doesn't mean that it is, but the evolution should be because of that.
Okay, my last question is connected more to the morphologies. So you have not explained too much how you have made such morphological analysis. So because you are tracing very different redshift.
Yes.
And so you didn't say that if you were using different filters, because I have seen so beautiful mergers being transformed into nice spirals when you change the the filters. So can you explain a little bit more what you're doing?
Yes. So at the moment, and the results I've shown, they're mostly from HST morphologies in the sort of that wide band around Z band, Z and Y. And that's been used for all redshifts. And I would argue that that's particularly an issue for redshift 1.5. And that would be a huge issue for redshift 2.2, which that's why I didn't even show the results. Because at redshift 2.2, you're basically looking at UV morphologies, and then you'll probably classify a lot of things as mergers, and then you see sort of the rest frame optical, and they're disks. They're just sort of very sort of unstable. So the thing we're doing at redshift 1.5 is that we have a very large sample with IFU observations, and the other thing is that we're complementing with the areas where candles has data, so we can at least compare the morphologies that we get from sort of Z band to something which is more rest frame optical. So at the moment, these results have been obtained with a computer algorithm, which was well calibrated up to redshift about 1.2 in Cosmos. But we are doing the proper analysis and making sure we eliminate all biases. Yes.
I want to come back to the extinction. The empirical result of the extinction doesn't seem to depend on galaxy luminosity. It's an interesting result, and it also, of course, makes your work easier. Nevertheless, how do you understand it? Because higher luminosity implies higher star formation rate, which implies higher metallicity formation rate, which implies higher dust content. So how do you explain the fact that the extinction doesn't vary with luminosity?
I think one part of the answer is it does, and I guess this was sort of showing it, is that the trend is there, and we're working on something with looking at the properties of these galaxies with Herschel, and we can show that much more clearly. It does depend on luminosity. But the dependence on luminosity, even at redshift 0, is not that strong. The slope of this thing is not that very strong. And it's also not very strong because this is a correlation with observed ones, right? So the thing is, you're observing something that's dust extincted. So it sort of diminishes any correlation that exists to begin with. So once you correct your H-alpha star formation rates, then this becomes even more obvious, because these things here are going to be more dust obscure, so they're going to get higher and higher. So this then becomes something like this. What I said is that the relation doesn't hold in the same way. So it's not the same relation as a function of H-alpha luminosity. There seems to be an evolution which is tracing the general L star evolution. But the other thing is not that strong in the range that we're looking, that we would be completely worried in terms of the H-alpha luminosity function. But I'm aware that it will produce some sort of flattening. So the most luminous emitters will probably be more dust extincted than 1 magnitude. So your bright end will go in this way a little bit.
Okay.
But I guess how much? Well, that's the other thing that we're doing, is we're getting spectroscopy. So we're getting Balmer decrements on the most luminous ones. So then we'll know.
That'll help.
Thank you for this. Has been a very beautiful talk, and you have touched many things which are very important, and you have linked them, all of them very. However, there is a thing that I don't know if you have thought of doing, is the fact that, you know, this famous Maddow plot, when you happen to do different galaxy masses, beams, you have that the behavior is not the same, right? This Heavens et al. Paper, famous one. And the analysis you are doing, you are somehow separating the star formation and the mass assembly, so to say. And that is clear in the analysis you have done concerning the environment.
Yes.
All right. So what I wonder is, wouldn't it be possible to do a similar study, but taking different masses beings? Because it would be nice to see a sort of relation between mass assembly and star formation. And that may happen just for low mass galaxies and not for the big ones. So this is something that could be interesting. I don't know if you are thinking and doing, but
yes, it's something we'll be doing next. Yes, it's something we've been thinking about, but we've literally, so this large sample over all these cosmic epochs has been finished very recently. So the paper was on Astrofísica last week. So this is something that we can now do now that we have the samples. It's a very good idea.
Could you explain a bit how do you compute star formation rates from the luminosity, from the H-alpha luminosity function? What is the kind of receipt that you use?
So we use Kennicut. We use the Kennicut relation to do that.
Yeah, but your luminosity function, you mentioned that high luminosity n is not important. And so I guess that the low luminosity n is important.
Yes.
And so when you cut the luminosity function where you start with and all these kind of things should be important. Could you comment on that?
So the thing is, because we're confident that we know the phantom slope and we don't really see it changing, we fix it, and this is integrated over the entire luminosity function. We don't do a cut. So for any given epoch,
to zero luminosity, basically.
Yes. Okay. I guess the thing is, once you go down to, I think it's about 10 to the something 30. It doesn't really. The other part is, even with this phantom slope of -1.6, it's not going to make a huge difference. So effectively, you could cut it at a much higher luminosity than 0. It wouldn't change the results dramatically.
Okay.
Hi, very good talk, thank you. One question, when you derive the H-alpha attenuation from the relation of O2 luminosity versus H-alpha luminosity,
yes,
you have to assume one metallicity for your galaxies, I think. So
yes.
What metallicity do you assume?
So what we've done is we've used SDSS and the range of metallicities there are in SDSS to do it. And what we've done is also quantify how different it would be for a range of metallicities. And this relation, it works sort of reasonably well within subsolar, solar, a little bit supersolar. It breaks down for sort of very supersolar and very subsolar. But from the spectroscopy that we have from IFU and from looking at H-alpha to N2 and also O2, O3 and H-beta, our galaxies are slightly subsolar. So in the regime where the relation that you'd get from SDSS still holds. But of course, the thing is, and that's why there's such a big scatter. I don't know if you can show it. Well, in any of these relations, you see a very huge scatter. So you wouldn't trust individual measurements in that way. But I think it's still a good way to look at statistical properties of the population. Because if you look at sort of a large enough galaxies going into the bin, then they'll probably cancel out the effects of slightly higher and slightly lower. But on a galaxy by galaxy, you shouldn't do it unless you know the metallicity, and then you can do it.